So there is a failed combustion. So we can circulate the air like swirling motion, so that the air carries the fuel droplets. Then the oxygenation takes place. Right? Then the fuel droplets surrounded by the, so that the heat transfer takes place. Then it attains the combustible rate. So immediately there is the at the various locations. Right? That is the idea of the CI engine combustion. Yes, it is air motion. So the air entering into the combustion chamber. So it is rotated as about the vertical axis of the cylinder. It is called the swirling motion. When the piston moves, because of the slope of the boat, the entering the combustion chamber, and it is rotated about this axis. So it is a swirling motion, right? So already it is a swirling motion. Then it is a compression moves from bottom right side of droplet center. Then this air is compressed. So because of the shape of the combustion chamber, right? So here this compressed air rotated with the perpendicular to the axis of the cylinder. Squeeze motion. So swirling motion occurs when the piston moves in a downward direction. There is a suction swirling, and the squeeze motion occurs during the compression time. Right? This increases the combustion rate. Right? It decreases the ignition timing. See, this is the space structure. The fuel is injected in the form of fuel droplets. So the most portion is the leading trailing edge. Right? Because of this fuel is injected radially into the combustion chamber. Right? So the air molecule, so that the air molecules carries the fuel droplets. Because of fuel is it disintegrates in small droplets. Right? So the air molecules takes the fuel droplets and surrounds the fuel droplets. Then the heat available in the air molecules because of the higher the attains the ignition temperature. Then the heat transfer between the air molecules and the fuel molecules. Then it attains the ignition combustible rate. Then combustion starts. See the second figure. There are many. Right? So various places the ignition occurs. Okay. So here there is the core is the center part of these fuel droplets, and trailing edge is the top one. So in the trailing edge, that is the diameter of the droplets is the bigger, and the leading edge, right? The leading edge, the diameter of the droplets is very small. That's why it is easy to form the combustible range. So first combustion starts in the leading edge. Then due to this temperature, slowly the heat is transferred to the trailing edge. So this is the mechanism of combustion. Okay, I hope you understand what is the difference between the SI engine conversion and the fuel conversion. So in SI engine conversion, there is only one definite flame travels across the combustion chamber. Okay, but in case of CI engine, there is no definite flame. Right? Various places the ignition occurs, then the sudden pressure increases. Effect of air motion. What are the effects? So mix injected fuel droplets with air motion. Right? Fuel droplets of different sizes. Without the circulation of the air, there is no atomization. Suppose in case of SI engine, already it is atomized outside. After injection, only the atomization. So the atomization increases because of the swirling motion inside the combustion chamber. And distribute the fuel droplets uniformly in the air charge. So we can distribute the air fuel droplets uniformly by circulating the air. So assist combustion of fuel droplets. To supply some fresh air to the interior portion of the fuel droplets. The interior portion supplies the fresh air. So we are circulating the air, so it is not supplying the fresh air to the interior. of the droplets, right? So it's of the air. So there is a possibility of failure combustion. It increases the transfer to the droplets and thereby reduces the delay period. Okay, that is the advantages of air motion. Decreases the delay period. So while decreasing the delay period, then the combustion, right? The proper combustion happening. So air should move in a smooth right angle to the direction of the jet. Suction swell, space motion, already told you what is suction swell and the space motion. See this figure. See this one. So the figure A, based on the slope of the inlet core, accordingly we can get the swelling motion. And there is some masked valve. Some portion is masked, some portion is closed by using some. Right? Then it will rotate the, you can create the swelling motion. Like it. So there are different arrangements, you can create the swelling motion. There, see here also the slope of the inlet core, and we provide some mask, then the air is rotated. And space motion, see decrease in space motion. So when the space motion occurs, when the piston is moves from VDC to TDC, that time it's compressed. So the clearance above the piston, right? If increasing the compression ratio, then what about the clearance volume? It's very less, right? So clearance above the piston, you can decrease the clearance above the piston by increasing the compression ratio. So it increases the space velocity. For example, see this figure, the graph, space velocity versus there is a decrease. See the space velocity nearer around 10 degree before TDC. 10 degree before TDC. What is this? See the clearance above this is 0.5 mm. Then the space velocity is around 50, right? The clearance above the piston is 1 mm. Then what is velocity is around 35. So like that, we can decrease the clearance above the piston, we can increase the space velocity. If we increase the space velocity, then automatically the combustion rate increases, right? And we move to the stages of combustion in CAE. Stages of combustion is normally discussed. That is the ignition delay, then propagation of fuel, then after burning. But here there are 4 stages. One is the ignition delay period, then pre-mixed combustion, then rapid combustion after burning. See, the fuel is injected. When the piston compression takes place, at the end of the compression, around 20 degree, right before TDC, the fuel is injection starts. The fuel is injection starts at 20 degree before TDC. Once the fuel is injected, so immediately they won't burn, right? So there is how it happened, right? The fuel is keep on injecting. Right? So where the fuel is injection end, it takes some time. The fuel is injected, then the injection ends around the takes 0.001 second, right? So that the fuel injection ends at this point. So once the fuel is injected, right, it takes some time to prepare the ignition. That is the prepared ignition delay period. So this ignition delay period, there are many reasons. Right? Because of the nature of the fuel, pressure of the system, temperature of the air, space motion, swelling motion, compression rate. So there are many factors. Once the ignition, then it's the combustion starts. But it is for the, once the combustion starts, all the fuels not burned at the same time. Some of the fuels attain the ignition points already told you. Then the sudden pressure rise. So is the uncontrolled combustion. Sorry, that is the pre-mixed combustion. Right? Because of the small portion of the mixture only attach the ignition point, then the pressure is increases. After that, right, the uncontrolled combustion. Sorry, this is uncontrolled combustion. So suddenly increases the pressure. After that, it's a controlled combustion. So maximum amount of fuel attains the ignition temperature. So the system is controlled. Okay. Also at the same time, it is in the exhaust system. Okay. Then the remaining part of the fuel, right, it's burned. Then it's the slowly the heat liberation increases. It's the controlled combustion. And only same thing, there is small amount of fuel only available. On the amount of heat liberated also decreases. Then the curve comes like this. Okay, this is the stages of combustion. And here the knocking, right, detonation or knocking occurs before the TDC at the time of combustion, because of the sudden pressure rise, so that there is the vibration, the vibration takes place at that time. Right? So this detonation of knocking, right, occurs because of the how much time it takes the delay period. The delay period increases, it accumulates the more amount of fuel. Then this fuel suddenly burned. Then if you decrease the delay period, you can control the detonation. Because of the small amount of fuel only accumulated there, then the pressure rise also decreases. This is the rate of heat release versus current angle. See, up to A, the start of injection. Right? Around 18 degrees before TDC, the fuel is injected. So there is no combustion, there is no releasing of heat. So once the fuel starts combustion at point B, suddenly the rate of heat release rate increases. Because of the sudden releases the heat, sudden combustion. Right? After that, so this up to this again the controlled combustion. Right? That's the controlled combustion. Quantity of fuel only available. Okay. So you see the end of injection after TDC. So it takes how much degree? It's like 18 to around 20 degree. Right? 20 degree crank angle takes the fuel injection. So the later part, during the means after previous combustion, even the fuel injector injects the diesel, then this fuel, right, so this fuel attains the ignition temperature very quickly. Some temperature is very high, already combustion happening. That's why it is the controlled combustion. Okay, then the late combustion, again there is no fuel available, then the very small amount of energy released during this time late combustion. Like this, then the ignition delay, what are the parameters? Right, what are the parameters affect the ignition delay? Okay, so there are physical process and a chemical process. The physical process, depending on the injection, atomization of the chemical reaction conditions. Spray atomization, evaporation, and mixing of fuel with the cylinder air. That is the physical delay. What happened in the SI engine? Right, the physical delay is 0. Because of already this evaporation atomization the outside of the cylinder by compressor, right? Sorry, carburetor. So the physical delay for SI engine is 0. But here the physical delay takes more time. Once the fuel is injected, there is a physical delay. Right? So good atomization requires high fuel pressure. Right? How the atomization because of high fuel pressure? Hole diameter. So that we can increase the injection velocity, injection pressure. So what we have discussed also. That's why this is a biodiesel. right? It's not mixed thoroughly because of higher than the diesel. Okay. So, and also the higher cylinder pressure also increase the good atomization. And the rate of vaporization of the fuel droplets depends on the droplet diameter. Right? Already I told you the droplet diameter of the leading edge. Topmost one, see this one. Yeah, this one. Sorry, the trailing edge, the droplet size is bigger, the leading edge droplet size is smaller. So here there is the evaporation takes place very quickly, atomization takes place very quickly. So here the leading edge, the trailing edge, the larger droplet size, the atomization does not happen very quickly. That's why the heat is transferred from the edge to trailing edge. Right. And the chemical delay. So chemical delay, once the physical delay is over, then the flame, right? The flame slowly starts moving. That is the chemical delay, right? So chemical delay is longer than the physical delay. So once this is physical delay, so the higher temperature, physical delay is longer than the chemical delay. So the total delay period in case of CA engine, physical delay plus chemical delay. The physical delay is very, very high compared to chemical delay. Once the physical delay is over, then immediately it will burn. So it takes more time. So the SI already told you, SI in the physical delay is almost 0. The objective value would be fuel quality. So for example, the CT number, it says the quality of the fuel. Suppose the higher CT number, the ignition quality is very good. So what is the CT number of diesel? Around 40 to 60. So gasoline is 20 to 10 to 20. Right? So that the diesel engine is not suitable for diesel engine. Okay. See, there are different CT number fuel, CT number 30, CT number 40, CT number 50. Right? So what is the CT number 50? How much? The pressure is around 60 bar, 70 bar. But in case of CT number 30, what is the pressure? And also this knocking, right? The higher knocking. And it's damaged the engine. So the CT number is 50. This is the maximum pressure, the ignition quality. CT number is higher, if you get the more pressure, but it's a vibration takes place. That is the drawback. And the injection pressure also increase the injection pressure. Then we can reduce the delay period. And also injection timing. The delay period increases with increase in injection advance angle. Advance angle. If you can advance the angle, normally the fuel is injected 20 degree before TDC. Suppose you inject the diesel at 30 degree before TDC. When increase the injection angle, then automatically recommended more fuel. The delay period. Okay. So optimum injection angle is 10 to 15 degree before TDC. Increase the diesel will result in increase in the delay period. Means we take air temperature pressure. See this one. The injection advance with the effect of injection timing 30 degree before TDC and 20 degree before TDC and 90 degree before TDC. For 90 degree before TDC, what is the pressure? It's a 60 bar and 20 degree 18 bar. Sorry, that is the pressure 80 bar. So that if you advance the ignition injection timing, right, you can increase the pressure. Increase the pressure. At the same time, you are losing the performance of the engine. And also this is a compression ratio. So increase the compression ratio reduces the delay period. See this graph, compression ratio versus temperature. So this is the minimum auto ignition temperature and the maximum air temperature. So minimum auto ignition temperature, right? It's the compression ratio, increase the compression ratio, the temperature is around 500 Kelvin. The maximum temperature 1000 Kelvin. And the ignition delay increases the compression ratio. So increasing the compression ratio, right? What is the compression ratio? 16. What is the delay period? The ignition delay. Right? If you increase the compression ratio, then the delay period decreases. Similarly, load. Right? If you increase the load, the delay period decreases. Engine speed. If you increase the engine speed, again the delay period decreases. Already we discussed this one. Okay. So not in diesel engine. See, if the delay period is long, a large amount of fuel will be injected and accumulated in the chamber. Perhaps. So first, what is the delay period? The delay period is small. So very small quantity of fuel only accumulated during this time. If you increasing the delay period, then again the pressure increases, right? And a small knocking takes place. Increasing the delay period, the large amount of fuel accumulated here, so suddenly it's a combustion happening. Right? Then because of due to this many vibrations are knocking. So that we can reduce the efficient delay period to get the smooth operation of the engine. Take care of this one. So we can compare right, knocking in SI engine and the CA engine. So in SI engine, the knocking occurs after TDC. Because of the fuel injected, the flame travels across the combustion chamber in the SI engine. At the end of the charge, right? The end of the charge attains the auto ignition. Then the same charge also, the flame travels opposite direction. Right? But in case of CA engine, once the start of combustion, immediately this knocking takes place. Okay. The knocking tendency high in SI engine, low in CA engine. No pre-ignition CA engine. To determine SI engine is relatively easy to distinguish between knocking and knocking. This is the comparison. The self-ignition temperature of SI is high, so low. Delay period, SI engine, it's a long, and this is a short. Ratio right. Yeah. Can you able to see this one? Hello?
Yes, sir, it is visible. Yes, sir, it is visible, sir.
Okay, right, fine. Right. So the performance calculation of engine. For engine, already we discussed before the SI engine, CA engine, everything, right? Then how to test the engine? What is the performance? How to measure the performance? So that the performance parameter, indicated power, brake power, right? Frictional power, efficiency, mechanical efficiency, indicated efficiency, braking efficiency, effective pressure, indicating effective pressure, braking effective pressure, like these are all performance parameters. Based on this parameter, we can tell this engine is okay. It is a good, it gives more efficiency like that. So, see this diagram. So, in energy in fuel, right? So 100% of energy supplied to the fuel supplied to the engine, right? But see, once the combustion takes place, some of the energy is losses, some of the energy is dissipated to the environment, some of the heat absorbed by the coolant, some of the heat is exhausted through radiation, right? So what is the remaining energy available? That energy is called indicated energy. That is called indicated power. So the fuel, what is the chemical energy available by burning of the fuel, right? So this chemical energy converted to heat energy, 100% of heat energy. So this heat energy, right, available in the top of the piston in the form of pressure and temperature, right? But the indicated available energy, so because of losses, we subtract 1 minus 2, that is the indicated power, indicated energy. Right. So this energy pushes the piston in a downward direction. Okay. Then The power is transmitted from the piston to crankshaft. Piston to crankshaft. So during this time, the same amount of energy is not transmitted to the crankshaft. Some losses. What losses? Frictional losses and the bumping losses, some unattended losses. Right? So the frictional losses, how much is gone? So what is the remaining useful energy? So the 1 minus 2 minus 3, that is the remaining energy available in the shaft. That is called the brake power. That is called the brake power. What is the power available in the shaft? Okay. So mechanical efficiency, the brake power to the indicated power. That is the mechanical efficiency. So we can measure the brake power, indicated power by various formulas. Already we know this indicated power, Planck, Young Planck, brake power. Right? If we are using the pony brake, we will use this formula. Brake power is 2 pi nt by 60. If we are using the rope brake dynamometer, then we can use this W minus S by dB plus D by 60. Right? W is the weight and spring constant. dB is the diameter of the brake drum. Small d is the diameter of the rope. D is the effective brake diameter. Okay. So what is the frictional power? What is the frictional power? What is the indicated power? Then what is the brake power developed with this crankshaft? The difference is the frictional power. Okay. And the measurement of brake power, already the pony brake, rope brake, hydraulic dynamometer. These are the dynamometers to measure the brake power. Okay. So finally, I'll go to the performance of the SI engine. How to measure performance? Let's see in this case. See, heat, form of fuel, 100% of heat. Right? So around 35% of heat absorbed by the coolant, while the coolant is supplied to the engine to absorb the heat. So what is the remaining amount of energy? Again, it goes to the next level, around 65%. So the exhaust gas, right? The exhaust gas carries around 33% of heat. What is the remaining? Only 32% of energy only goes to the brake power. And also the surrounding losses. Brake power is at 20%. Right? So the efficiency is only 20% efficiency. And this is the heat supplied by MCP delta T, mass of the fuel and the heating value of the fuel. You can calculate and equivalent indicated power then Planck. And the heat carried with the cooling water, MCP delta T. So mass of water and the specific capacity of water and the temperature difference. What is the water in the temperature and outer temperature? Right? And similarly, heat carried with the exhaust gas. Right? And so bit of exhaust gas. And in the temperature, outer temperature of the exhaust gas and mass of the exhaust gas. You can find the heat carried with the exhaust gas. Then you can tabulate what is the heat supplied by the fuel in terms of percentage. It is 100%. Then heat absorbed by the indicated power. How much amount of heat absorbed only developing the indicated power? What percentage? Heat taken away from the cooling water. Then in terms of percentage, like that, it is equal to okay, are you hear me? Can you hear me? And the specific fuel consumption. Okay, fine. Mass of the fuel to the brake power. What is the specific fuel consumption? So brake specific fuel consumption, mass of the fuel by brake power. Indicated specific fuel consumption, mass of the fuel by indicated power. Right? How much fuel utilized for converting brake power? How much fuel utilized for developing indicated power? That is the brake specific fuel consumption and indicated specific consumption. The unit is a kg per kilowatt hour. The thermal efficiency, see how much power developed by the engine. With help of this, what is the heat supplied? So heat supplied is mass of the fuel, calorific value, heating value. So brake thermal efficiency, indicated thermal efficiency, indicated power by heat supplied, and brake thermal efficiency, brake power by heat supplied. Okay, the heat supplied is total heat supplied. Mechanical efficiency already brake power by indicated power, right? And astronaut efficiency, relative efficiency, okay, volumetric efficiency. So these things, see the energy. So see here the radiation, how much radiation because of the incomplete combustion it takes this much energy, and the exhaust gas around say 25% of energy, and the coolant takes around 30% energy. The useful work only 23 or 23 percentage. Right? And see this is the typical curves efficiency. The mechanical efficiency is the maximum. See the brake thermal efficiency, then integrated thermal efficiency, the specific fuel consumption. So specific fuel consumption the curve, see initially it is the higher, then the middle is the lower. Because of the engine running at the ideal when there is the cruising speed, this fuel consumes very less quantity of fuel. Right? The other side, the starting side, idling condition, right? The starting time, the rich mixture supply. So specific function increases. And similarly, the higher load, maximum load, then it consumes the more fuel, then slightly increases. And so also brake ineffective pressure versus load, right? Same brake ineffective pressure, brake has power, brake is due to consumption, exhaust gas temperature, torque. So you can plot the graph like this. And also the brakes similarly the different engine speed versus brake has power. Okay. See, this is one of the numerical, so the simple numerical. The petrol engine, single the petrol engine, the compression cost is 1.96. The fuel consumption is 7.2 kg per hour. Calorific value 43,890 kg. The air consumption 2.8 kg per minute and the speed 9,900 rpm. So torque 186 km. The cooling quantity of cooling water is 15.5 kg per minute. And temperature rise in the cooling water 36 degrees Celsius. So there is not given inlet temperature, outlet temperature. Temperature rise is given 36 degrees Celsius. The exhaust gas 10 degrees Celsius. The room temperature 20 degrees Celsius. Temperature of the CP gas 1.17. So we calculate the brake power. That is the consumption, brake thermal efficiency for the good value. So how to do the problem? So first see the brake power. So what is the given brake power? There are different methods. So what method they adopted here? So based on this given data, the torque on the brake drum is only 86 Newton meter is given. So torque is given. So then you can directly use the Crowley brake 2 pi nt by 60. See 2 pi nt by 60. So in conversion I am using the 60,000. So what is the speed and the torque? You can take the speed 1,900 rpm and the torque 126 Newton meter. You substitute here, you get the 37 kilowatt. That is the brake power. 37 kilowatt. Then what is the brake specific fuel consumption? Already you know what is the mass of the fuel, right, used for converting this brake power. So already you have the brake power and mass of the fuel. So mass of the fuel, how much is given in the question? 10.2 kg per hour. So here mass of the fuel 10.2 kg per hour and brake power 37. So what is the final answer? 10.2 by 37 kg per kilowatt hour it gets. And the brake thermal efficiency, brake power by mass of the fuel, the calorific value. So brake power 37 kilowatt. The mass of the fuel, see 10.2 here divided by 3,600. Because of see here the fuel consumption is 10.2 kg per hour in terms of hour. So here what is the unit of this one? Brake power, so kilojoules per second, kilowatt, right? So 1 watt is equal to 1 joules per second, so kilojoules per second. So it is in the second, but this mass of the fuel is an hour. So you convert this hour into second, 3,600, and the calorific value. So finally you get the efficiency is 29%. Okay, and this relative efficiency, brake thermal efficiency by air standard efficiency, that is the relative efficiency. So we have the brake thermal efficiency 29%. And the air standard efficiency. So this is the SI engine, right? This is the SI engine. So the SI engine runs in an Otto cycle, already we know. Then what is the efficiency of Otto cycle? 1 minus 1 by r power gamma minus 1. See 1 minus 1 by r power gamma minus 1. The compression ratio also given in the question. It's 1.96. So you substitute here, right? So gamma, so 1.4 minus 1 is a 0.4. So gamma per air, right? Then it gives me 0.56. Then what is the efficiency, relative efficiency? It's 51.76. Okay. So next, how to find out the heat balance? So first you find out what is the total heat supply.
No.
Also, yes.
Where are they?
Hello. Hello, sir. Any doubt?
No, sir. It's okay.
Okay. So heat supply, mass of the fuel, total heat. So what is the total heat, mass of the fuel? And the caloric heat value already is known, 49, 43, 890. And mass of the fuel, see? So you have to here you calculate the kilojoules per minute. Right? So that 10.2 by 60 only, right? But yeah, you see here also you convert this kilojoules per. So it is given the question kilojoules per hour. So you convert to kilojoules per minute. So that it is in the 60 divided by 60. Then you will get this value around 7461.3 kilojoules per minute. It's 100% of heat. Then heat equal to brake power. What is your brake power? 37 kilojoules per second. Right? You convert it to minute, you multiply with 60, it comes around 220 kilojoules per minute. It comes around 29.7%. Okay. From the total heat. Then heat equivalent to cooling water. So already we know MCP delta T. So mass of water and specific heat capacity of water and the difference of temperature. Right? The difference of temperature is given directly 36 degrees Celsius. 36 degree. Either Celsius or Kelvin both are same. The difference is same. So mass of the fuel is 15.5. Mass of water 15.5 is given. Right? 15.5 kg per minute. So we can use the 15.5. And Cp of water already we know 4.18. Then difference it comes around 3 kilojoules per minute is around 31.2%. Right? So the cooling water absorbs more amount of heat than the power generation. So what is the efficiency? 29.7. So the cooling water takes are more than Indian efficiency. So the maximum heat absorbed by the cooling water. Right? The heat equal to exhaust gas in the formula. So mass of exhaust gas and Cp of exhaust gas is delta T. See the mass of exhaust gas, the combination of fuel and air. Right? So how much fuel is used? Mass of air plus fuel. Mass of air. And mass of air is 3.8, right? Mass of air 3.8 kg per minute. So you can use the mass of air here and the 10.2 kg per minute, right? And the Cp of the gas is given and the difference of temperature, right? Gas exhaust temperature and the atmospheric room temperature. So finally you will get 1811 24.2, right? So you can turn it here, it comes like this. Right? Yeah, similar problem you can do like this, same time, and this is the one of the most stressed problem. Okay, next I'm going to do the ignition system. So ignition system, it is for SA engine. Why spark ignition? What is the reason spark ignition? Because of the compression ratio is very low, compression ratio, and also the self-ignition temperature of gas is high. So because of this, we go for the ignition, right? The self-ignition temperature is very high. That's why we go for the ignition. It is not possible to compression. Even if you increase the compression ratio, it is not possible. It cannot attain that self-ignition temperature. So what are the requirements of ignition temperature, ignition system? So ignition takes place at the end of the compression. Right, at the end of the compression only the ignition. So that we can fix like this. Set the system. There is no missing of cycles due to spark failure. Sometimes the failure may occur, right? Sometimes, right? The failure. So it is not accepted. So there is no missing of cycles due to spark failure. How many power strokes? Around 200 power strokes. Some cases, 190, 10 missing cycles. Okay. So So only 190 power strokes like that. So ignition should give you energy to start and sustain the burning. Right? So the ignition, it gives you this much amount of energy to sustain the burning. Ignition will supply minimum energy required to start within a small volume in a very short time. Because of the spark plug is located there, the clearance volume is very much less. Right? So that if, there is a small volume available, so that the ignition system to supply minimum energy in a short span of time. And we should adjust arrangement of source spark with speed and load conditions. With speed and load conditions, arrangement can change the sparking adjustments. There are a spark ignition and a coil or battery ignition system, mechanical ignition system, electronic ignition system, transfer system. We go through this because of this one of the battery ignition system. There are primary windings, secondary windings, connected primary windings connected to the battery. Right, so the primary turns and the secondary turn, number of turns is very higher in the secondary winding. So it is connected to the contact breaker. So once this supply is given, so it plugs like the breakers. Then accordingly, this energy is supplied to this distributors, spark plug. So based on this, the sparking takes place in the cylinder. See, it consists of 6 to 12 volts battery. The ignition coil I told you, 200 to 300 turns of thick wire. And secondary winding, 21,000 turns within the wire. Okay. Okay, so this is very important. The sequence of order, firing order. For four cylinder, this cylinder is the 1342 or 1432. That is the firing order of a engine. And firing order of the six cylinder in line is the 153. 15363. This is the firing order of the six cylinder engine. Okay. So next we move to lubrication system. Because of the engine, there is the mean number of moving components. Okay. Because of the moving components, there is the friction. So due to friction, it affects the performance. For example, the piston and the cylinder. The piston and cylinder moves in a very rapid manner. So due to friction, the size gets, the piston size gets decreases, the cylinder size gets enlarged. So that we provide the reduce the friction resistance. That's why we provide the lubrication, right? And we will improve mechanical efficiency, protect the engine against wear, serve as a cooling agent by picking up heat. Because of the circulating lubricant, it also acts as a coolant. It absorbs the heat generated during the conversion. So remove all impurities from the lubricated region, right? So form a seal between piston rings and cylinder walls to prevent blow-by. Right? So this lubricant forms the seal between the piston rings and cylinder walls. If there is not seal, because of this due to this gap, the fuel mixture directly goes to the crankcase. That is called the crankcase blow-by. There are different lubrication systems. Mist lubrication system or is a petrol lubrication system. And a wet sump lubrication system and a dry sump lubrication system. So what is a mist lubrication system? It's employed only for two-stroke engines. For wet sump and dry sump, this is used for the four-stroke engines. So mist lubrication system, see, around 3 to 6% of oil, right, added to the petrol tank. Already we know, right, there in the two-stroke engine, 3 to 6% of oil, right, added along the petrol. Then this acts as it forms the carbon. Then this carbon deposited on the carbon, the rubber lubricate all the parts. Okay, so piston rings and other parts. The main advantage of the system is very simple. The low cost system does not require any oil pump or filter. Because of this, fuel tank is located very higher than the engine cylinder, right? So automatically, due to the gravity, the fuel flows from petrol tank to engine. There is no need of any pump or filter. That is the advantages of mist lubrication system or pet oil. Petrol mixed with 30% of oil. And it's a wet sump lubrication system. So here there is the sump, oil sump. It is the crankcase, right? So there is an oil strainer, the pump, it pumps the lubricating oil. Right? So oil proud is there. Right? So in the bottom of the crankshaft, there is a scoop attached in the bottom of the crankshaft. While rotating the crankshaft, when the crankshaft comes bottom, it takes the oil from the oil tank, that is the oil probe, and sprays to the all the oil components. Right. So it wets on with the bottom of the crankcase contains oil sump, right? So oil dripping from the cylinders and the bearings flow, right? Gravity back into the sump. Again, due to gravity force, again come back to the oil sump. So this is used for the that is the living capacity engines, wet sump lubrication system. So here the oil pressure gauge is measured the pressure in the okay. And this is the splash lubrication system. Similar manner, this is also wet sump lubrication system. See, the scoop, right? The scoop takes the oil, and also there is one oil, there is a pipeline, right? So through this, the oil is close to the system, some pressure system. So the pump pressure the oil, lubricating oil to the various parts. So it's and this is a full force feed system, so there is no splash here, and all the moving parts like the bearings, right, the camshaft, all the moving components connected. So there is a hole, right? The holes are built. The sump, so the pump supply the lubricating oil to all the moving parts. So this is the effective lubrication system, and the dry sump lubrication system is used for the stationary engines, right? Stationary engines we go for the dry sump lubrication system. And see, there is one dry sump available here. So there is the pump, it takes the lubricating oil, right? And it controls the pressure and the filter into this. Finally, it goes to the day supply tank. So from the day supply tank, the pump takes the lubricating oil to the supply to the engine. So because there is an oil cooler, it reduces the heat. So here, after that, so this from the engine, then it is again resupplied to the dry sump. So the fuel is not directly supplied to the dry sump to engine. So we can save some amount of lubricating oil to the supply tank. Always it is ready. Right? That is the dry sump lubrication system. Properties, already we discussed the class 1.5 point. So these are all important properties of the lubricant. We have discussed the resistance to flow, that is a viscosity. And the flow point, the temperature, what temperature the fuel will flow. That is the flow point. It's a very important property of diesel fuels. And the flash point, fire point, right? And the rating of the lubricating oil is very important. Right? Finally, we discuss the scale. That's what we are saying. So the oil lower viscosity there is a less viscous, lower viscosity, less viscous. Then is a higher viscosity. So usually the cold weather kind of operations, so modern high temperature, high speed, close tolerance. So see, this oil have low viscosity grades when they are cold, and the higher are it becomes hot. For example, SAE 10 W30 grades, 10 for the winter, it's a cold. So 30 means when it is a hot. That is the specification of lubricating oil. So some of the types is given here. And the lubricant, see, the lubricant additives.
Excuse me, sir. Sir, you have explained 10 and 30. 10 degree means minus 10 is there?
No.
That it retain its viscosity at this temperature?
Yeah,
This is the meaning of that, na?
Yeah. SAE 10
so 10 winter, you have given an example here that SAE 10 W30.
Yeah. Yes.
So
That is the
means
cold.
10 is a that is a
10
temperature.
degree,
10 degrees.
temperature.
So winter means minus 10 degrees, sir. It means that, or no, simply 10 degree.
No, not minus
Uh,
10 degree. It is
it,
simply 10 degree.
okay.
Only. Because of minus 10
Okay.
degree, the fuel will not flow, That's
Yeah,
why.
that's why that I want to clear from you. Okay,
This
so
is the.
these are simply plus 10 degree and 30 degree
Yes.
to retain its viscosity.
Yeah, I'll discuss it.
Okay, sir. Thank you.
Okay. And the lubricant additives, for corrosion and rust inhibitors, anti-foam agents, detergent. You can add these additives to increase the lubrication. Right? Animal vegetable minerals with that already you know this. Okay. So after this is a lubrication system. Then the cooling system. What is the necessity of the cooling? Right? We can reduce the temperature of the system. That's why we work for cooling system. Because of the combustion, right? The large amount of heat liberated. So we need to reduce the temperature of the engine. That's why the cooling is very essential. Right? So what is the reason to promote the high volumetric efficiency? That also one of the important. And so the proper combustion, that is the reason for cooling. So the effect of overcooling. See, the thermal efficiency decrease due to no loss of heat carried by the coolant. Suppose we circulate the coolant, right, absorb more amount of heat, already we discussed, right? But around 33% of heat absorbed by the coolant. That's why the efficiency gets decreases. And the vaporization of the fuel is less, resulting in lower combustion efficiency. More cooling, then vaporization is not happening. So that we can maintain the average, there is an exact temperature, what temperature we maintain. The low temperature increase we discussed that we can causing the more friction. So that we maintain the optimum temperature. That is a method of cooling, air cooling and the water cooling. So air cooling, see in case of the two-stroke engine, already we know the two-stroke engine. So that is the engine, the fan rotates before the engine. Then it's the air, natural air flows through the puts the many fins provided in the two-stroke engine. So the air separated through fins and it puts the engine. So it is used for the two-wheeler vehicles. Right? It's not an air-cooled engine, it's used for only light vehicles. And this is also one of the air-cooled engines, one type. And there is different types of fins. So this fins absorbs the heat, so the heat is dissipated from the engine to outside. Based on the fins type. And the liquid cooling, see, there is some coolant from the engine, right? So this coolant separated through the engine. Then it absorbs the heat, so that it reduces the temperature. And this is the thermosiphon system. So here there is no pump. So here there is the engine, which is connected to the radiator here. So because of the warm air, right, warm temperature goes up, and this because of the higher density of the water, right, it comes down. Right. So based on this arrangement of this system, automatically the coolant flows to the engine and it gets back to the radiator like this. Right. So this is the thermosiphon system. And this is a forced circulation system. Normally we have this type of cooling system. So there is one pump system, right? Because there is one radiator. So there is a coolant separated to the individual components. So it absorbs the heat. Then this coolant again goes to the radiator. So before that there is one thermostat valve is located here. So the functional thermostat valve, right? It never allows the low temperature coolant. Right? Once it attains the normal temperature, then only this thermostat valve will open, then this coolant will go to the radiator. So that is the purpose of this type of cooling system. Yeah, this is the thermostat. Right? So it is a cold engine, the cooling water never enters into the radiator. So here the thermostat valve is when it's closed. Once it attains the normal temperature, then only it opens, then the cooling coolant enters through the thermostat and it goes to the radiator. And this is one of the evaporative cooling system. But based on this evaporation, this will cool. So the system engine will be cooled because of the evaporation of the water in the cylinder jacket. Right? The evaporation. Because of it evaporates, it absorbs heat automatically evaporates. So the system is used for cooling many types of industrial engines, high capacity engines in the evaporative cooling system. And some of the antifreezes, right? So due to the very cooling climates, right, the coolant get freezing maybe takes place, right? That's why the antifreezes to maintain the coolant to freeze, right? That is the purpose of these antifreezes. And the lubricating oil also coolant, already discussed. Okay, up to this is okay. So, what's the time now? Right. Do you have any doubts? I can clarify you. And also I can show some of the, beyond the subject, I can show you. Okay, up to this, you have any doubts, you will discuss. Then I have some of these slides, and then I can show you the slides also for even research purpose. Can you see the slide again? Hello?
Yes, sir, visible.
Okay, right.
It is written here fuel properties.
Yes, fuel properties. So, now we will discuss the fuel properties also. Some fuel properties. What is the fuel properties? See, the chemistry of the petroleum, see the crude oil elements are carbon equal 18%, hydrogen 12 to 14, and nitrogen this much 0.10, sulfur this much, oxygen this much, right? So, this is the composition of the crude oil. So, the major contain carbon and the hydrogen. That's why it is called the hydrocarbon fuel. And this is the boiling point of range, right? So diesel fuel is 180 to 240 degrees Celsius, right? The gas is 22 to 200 degrees Celsius. So this is the refinery at this temperature the gas will get, right? And see, this is the specification of BS norms for a gasoline. So what is the BS2? The density is 710 to 770, but BS4 710 to 775, right? And some important properties I'll show you. Yeah, see, sulfur content. What is the sulfur content? 0.05, 50 mg per kg per BS4, and anti-knock octane number is 84. Motor octane number is 81 for this one. Yeah. So in case of diesel specification, see, this is the diesel specification. CT number for 51, BS4, and 48. And important property, yeah, this is the important properties of this specific gravity. Suppose we go for ethanol and methanol to reduce the emission level. So what is the diesel gasoline 0.72 to 0.75, so ethanol 0.79, methanol 0.79. So almost is matched with this gasoline. And also see boiling point 85 to 437, ethanol 173. 139. Okay. And the heating value is 18, so what is the 43.5 gasoline and the ethanol 27, ethanol 20. So almost is the 50% of heat of the gasoline. And what is the most advantage we are using ethanol or methanol as a fuel? See, the octane number C, 111 for ethanol, 112 for methanol. What is the octane for gasoline is 91 to 100. So if we are using methanol as a alternate fuel, then the ignition quality is improved, right? The octane number is the ignition quality of the fuel, right? So we can improve the ignition quality by adding this ethanol and methanol certain percentage. Around 5 to 10% ethanol as a mixed fuel gasoline. Okay. And the CT number is below 15 for ethanol, so that it is not used for the diesel engine. The CT number 40 to 60, so it is not suitable for diesel engine. And see, I can show you some of the properties of the natural gas. These are all alternative fuels. So natural gas, hydrogen, ethanol, diesel, and gas, and they can compare. See what is the heating value? Heating value of ethanol 26.8 electrode per quart, and the hydrogen 120. So that you can use the hydrogen as a fuel. It's a clean fuel. You can use hydrogen also. And this is stoichiometric actual ratio for ethanol 8.9 to 13.7 diesel, the gasoline, natural gas. So we can use as a natural gas in a SI engine. Right? Okay, see emission, yeah, it's very important. So what are the emissions? Right? So the causes the global warming, acid rain, smog, right? And see, what are the engine emissions? Then unknown hydrocarbon, oxides of carbon, CO2, oxides of nitrogen, oxides of sulfur, right? These are the emissions. And what is the non-exhaustive? Unburned hydrocarbon from the fuel tank is global. That is a non-exhaust emissions. So this is the exhaust emissions leave from the engine tailpipe. These are non-exhaust emissions leave from the tank. Suppose we park the vehicle for a long time, then the fuel gets evaporated from the fuel tank. Right? But also the fuel pipeline, fuel flows from the fuel tank to various places for the fuel injection. Then some losses. So that are the non-exhaust emission. You see, these are the emissions. So evaporative exhaust emissions used from the tailpipe, and evaporative emissions, see, because of hot soap, running losses, driving losses. These are the non-evaporative emissions. See the unburned HC formed, unburned hydrocarbon emissions because of mainly incomplete combustion. Right? See, this is the range of hydrocarbon. Gas tank 10%, carburetor 10%, practice flow by 20%, exhaust 25%. Right? So the exhaust gas contains 55% of the unburned hydrocarbon. Okay. So because of what is the reason? Because of the actual ratio. Right? Because of the rich mixture, it provides the more HC. Because of the incomplete combustion. Improper mixing. So these are the some right points, factors for developing the unburned hydrocarbon. And a lubricating oil where you mix with this oil, that is the reason for HC emissions. And the Crevitz volume. So what is the Crevitz volume? Some narrow volumes present around the surface of the combustion chamber. See this figure. Yeah, this is the inlet valve, the exhaust valve. There is a small space available in the seating of these valves as well as the cylinder, right? So the fuel is right occupied this space. So this fuel never burned. So this is the Crevitz volume, and there is a piston and a piston rings, small gap. That gap, the fuel is occupied there. That is called the Crevitz volume. So these are all the reason to increase the HC emission. Okay. Yeah, see, this is the curve. See, this is the equivalent ratio. So CO is this much value. So if it is a two lane, then the CO decreases, right? And also HC. So if increasing the fuel ratio, then the CO and HC increases because of the incomplete combustion. And the NOx values, NOx values minimum in terms of in case of rich mixture, the NOx values decreases. Because of the rich mixture, maybe incomplete combustion, the temperature of the system decreases. The NOx mainly depends because of the temperature. If it is the higher temperature, there is a more possibility of NOx. So that the NOx value, this is the maximum at it is in the stoichiometric condition. Stoichiometric condition, NOx is maximum. Why? Because of there is a complete combustion. Because of the complete combustion, the temperature of the system is increases. That is why the NOx value also increases. And this is also the effluent ratio. Then the CO formation. This is also incomplete combustion, maximum incomplete combustion, and because of rich mixture and poor mixing. Okay. And see, I can show you some of the result obtained from the using the catalytic converters to reduce the emission, right? I can show you the direct emission. How to see how to emission control technology, right? So there's some advanced fuel injection system and the particulates, right? Particulate traps. So NOx emission, adding additives, water injection, emulsion technology, some EGR, SCR, right? And low temperature conversion, low heat rejection, LHR engines, stoichiometry, that is the HCCA engine. These are the to reduce the NOx and the CRDI system, right? Fuel injection. There are multiple injection, port injection, for reducing the, increasing the performance. And see, I can show you, yeah, see how much amount of EGR added to the system, around 15%. So exhaust gas are recirculated to the engine to reduce the NOx. So these are the non-reacting gases, CO2, EGR, nitrogen, helium, argon. So it's readily available the exhaust gas, that's why we can use the exhaust gas as a medium to reduce the NOx. The exhaust gas, certain percentage, around 15% of exhaust gas recirculated to the engine cylinder to reduce the NOx. One of the methods. I can show you some, some alcohols also, ethanol, methanol we can use as a fuel. Yeah, see this one. Yeah, this is a graph. See, neat gasoline, 5% ethanol and 10% ethanol. What is the CO? For neat gasoline, the CO is a 0.78, right? And in case of unburned hydrocarbon, 0.45. Suppose if you are using 5% of ethanol, the CO get decreases and also the HC also decreases. If you have 10% of ethanol, the CO and the HC also considerably decreases. So this is the advantage, right? And see this emission from a multi-point fuel injection system. See, this is the commercial gasoline, CO, HC and the NOx. NOx. Then if you use for a 5% ethanol and for 10% of ethanol, CO, HC and the NOx also decreases. See the NOx value get decreases. So how do we decrease the NOx? By adding the ethanol certain percentage. So it decreases the combustion temperature. Right? And also see this is methanol and petrol. So the brake power, even if you increasing the brake power, we are using the methanol. So and also the compression ratio, see 8.2 and 13. So if we are using the petrol, this is what is the brake power? It gives around 40 maximum operation the 5,000 RPM. In case of the methanol, we use the compression ratio 8.2 to 13 to do the brake power. Okay, and similarly, this also the specific fuel consumption also less in case of using the methanol. Okay. 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 After this, I will stop. You can have any doubt, I will clarify you. Hello. And one of the students asked me to biodiesel, Yeah, I will show that that slide also biodiesel. I will show some. Yeah. Can you see this one? Vegetable oil and biodiesel?
Yes, sir.
Okay. See this vegetable oil we can use directly. We can use directly as a fuel in a vegetable oil in a diesel engine. But it is only for a short-term purpose only. It's not in the long term because there are many reasons, right? The viscosity, mainly the viscosity. The advantage of straight vegetable oils is readily available. You can use even the diesel, even with the diesel engine, running using the vegetable oil only in the initial stage. Later on, they found the gasoline and diesel and everything. Later on, only they tested the fuel. But initially, they manufactured the engine to run the vegetable oil. It's readily available, and there is no sulfur and a low aromatic content, so biodegradability, and CT number close to that of diesel. That is the advantage of vegetable oil, right? So heat content of most of vegetable oils around 90% of diesel fuel heat. Okay. So it is the oxygenated fuel, long chain saturated hydrocarbon, suitable for diesel engine. Around the calorific value, around 40,000. Even the diesel 45,000 kilojoules per kg. In vegetable oil, it comes around 38 or 40 kilojoules per kg. Okay. So what are the issues with the use of a straight vegetable oil? What is the drawback? So oxidation, gum formation, fuel line, and the filter clogging because of due to higher viscosity. Right? About 10% oil efficiency due to the effect of high viscosity and mixture preparation and conversion. So smoke exhaust emissions are higher because of due to higher viscosity. So incomplete combustion happening. That's why Hc and CO increases. Okay. So that we can go for the unprocessed vegetable oil. We face these issues. Suppose we can change the fuel, vegetable oil certain percentage with the diesel and alcohol. Then we can attain the almost equal specification of the diesel. Then we can use the fuel, vegetable oil as a fuel. So these are all the limitations. See, high viscosity, poor optimization, improper mixing, lubricating and dilution, high carbon deposits. These are all the many drawbacks if we are using vegetable oil as a fuel. To achieve, then we go for the blending that I told you. Then we convert this into biodiesel. So this is the physical properties in the properties of vegetable oil. Some of the example. See the corn vegetable oil. The kinematic viscosity is 34.9. For the diesel, it is a 2.5. So cotton 33.5. But the silicon number values is almost equal to diesel. The heating value also see 90% of the diesel. So this is the, and also the flash points are very high. So it is safer to use. Right? So only drawback the viscosity. So then how to reduce the viscosity? Then we go for the convert this into biodiesel. So there are many methods. Right? We convert into biodiesel. We can use the biodiesel. So biodiesel, we can reduce the viscosity. That is the advantages of making a biodiesel. Right? There is one process, a transesterification. The transesterification method using some chemicals, alcohols, ethanol or ethanol, and some catalyst, NaOH or there. Then we can manufacture the biodiesel. Then this biodiesel is equal, the properties of biodiesel are almost equal to diesel. Diesel as a fuel. Right? There are many raw materials, rapeseed oil, sunflower oil, soybean oil, palm oil. These are the raw material available. So for India, Jethro Karanja, right? It's a choice for India. Then produce the biodiesel using this Jethro Karanja. See, this is Jethro power plant. We can get the seeds from this Jethro fruits. Then it is this is the transesterification reaction. See, this is the oil fat. Then it's mixed with the alcohol. Diesel and the glycerol is the byproduct. Right? So the okay. Here it is told directly. Yeah, the specifications. The viscosity is 3.5 to 5. In case of the biodiesel, the methods DIN 510606. This viscosity, and the American Society of Testing Materials viscosity is 1.9 to 6. Almost the bio viscosities reach this 6 up to 6. Otherwise, we can mix with this diesel certain percentage, then it almost equal to the diesel viscosity. Yeah, see, I'll show you. See, certain number and the low sulfur, see, diesel, and see, rapeseed methyl ester. Methyl ester means biodiesel. Need a rapeseed oil, rapeseed ethyl ester. See here, the CT number is a flash point and the see viscosity. What is the viscosity? 2.98 for diesel. But the rapeseed methyl is at 5.65. Right? And the rapeseed oil, see, 47.6. So how much it decreases? See, because of a transesterification process, the vegetable oil is converted into biodiesel. Then the viscosity is drastically decreased, 47.6 to 5.65. Then we can use this biodiesel as a diesel, right? And similarly, rapeseed ethyl is 6.1. Okay, and see the combustion. Yeah, so combustion. See the heat of combustion, 46 or 20 kilojoules per kg, and see the ethyl is at 40. So almost 90%. I can show you some, impact of biodiesel on emissions. See, B100, in the sense B100 means 100% of biodiesel. We can use 100% of biodiesel. And B20, 20% of biodiesel and 80% of diesel. So D2 means 100% of diesel. When we take the performance test, then the HC emission B100 gives 84%, lesser than diesel. Okay, so there is a complete combustion takes place. And see, the CO also 41% lesser than the diesel. Suppose B100, B20 15% lesser than diesel. For HC it is 17% of lesser than diesel. For particulate matter 38% lesser than diesel. And B20 11% lesser than diesel. The only drawback, NOx. If you are using the biodiesel, the 10% higher than diesel. If you are using a B20, it is a 3% higher than diesel. Why? Because of complete combustion. Due to temperature increase, higher temperature. That's why the NOx value increases. Then how to reduce the NOx? There are many techniques, right? EGR, exhaust gas recirculation system, selective catalyst reduction techniques, right? And adding some additives. Like that we can reduce the NOx emissions. But the performance parameter almost equal. There is nothing different. Biodiesel and diesel almost gives the same efficiency. There is no much difference. Suppose a particular engine gives you 30% efficiency while using the diesel. In case of biodiesel, almost gives 30, or even some engines gives higher than diesel efficiency also. Right? Okay, I hope you understand. Okay. Right. I stop up to this. Any doubts? I can clarify you.
Dear participants, any doubt, kindly ask our research person, Dr. M.A. Aswagan.
Okay, some of the students give the feedback. Right, thank you.
Thank you.
You have any doubts, you contact me. I have given the mail ID to Professor Vijay Kumar sir. We will touch with you. If you have any doubts, we will discuss. There is no problem.
Okay, thank you, Professor, for the wonderful session you are handling.
Okay. Okay, thanks once again. Thank your management, Pearson College of Engineering Technology, for giving this opportunity. And thanks to all the participants for attending this lecture. I'm very much happy to share my thoughts. Thank you, Anurag.
Thank you, Professor. Thank you.
Okay. Okay, Professor, can I leave?
Yes, sir. Yes, sir.
Okay, thank you.